For our high-pass filter, again for the sake of completeness, let's take a look at how we can find out what the corner frequency for this particular function is. And previously what we've seen is that the transfer function for this high-pass filter was a little complex expression that was JWCR over 1 plus JWCR. And again, we'd like to represent this more in terms of what the magnitude function is and then what the phase function is. And so we're going to need to transform this rectilinear expression into a polar expression. Our value at the top, JWCR, if we were to plot that on a complex plane, would be at the point right here. So it would have no real component and just be WCR. So when this turns into a polar coordinate, what it's going to be is just WCR e to the j 90 degrees, because the length of this is just WCR, and the angle here is a 90-degree angle. In the same way, we're going to need to take the denominator here and replace this, and again, if we plot this on our complex plane, this would be at the point 1 WCR. And as we've seen in the previous examples, when this is turned into a polar coordinate system, this is 1 plus W squared C squared R squared, the square root, e to the j, and then it was the tangent of WCR, the tangent inverse of WCR. And so I can now rewrite all of this by saying my numerator is WCR over 1 plus W squared C squared R squared square root, and then our exponentials are going to be 90 degrees minus the tangent inverse of WCR. And so this expression right here is going to be my magnitude function, and this expression right here is going to be my phase function. To find the corner frequency, remember the corner frequency is when the power of the signal is at half power. And so this is when our magnitude function, our squared magnitude function is 1/2. And so we can take our magnitude function from the previous slide and plug it in here and square it. So this would be WCR over 1 plus the square root of W squared C squared R squared. We're going to then square all of that and set it equal to 1/2. And so if we square all of our components, W squared C squared R squared, and then, let's make sure we got this bit right, then this would become 1 plus W squared C squared R squared is equal to 1/2. When you rearrange all this, 2 of this large expression is equal to 1 plus this expression again. And if we begin to combine all of our terms, we find that W squared C squared R squared is 1, which implies that WCR is equal to 1, which when we solve this for W, we get 1 over RC. So again, it's the same corner frequency for both low-pass and high-pass filters when they're built as an RC circuit, and regardless of which transfer function you start with, you end up with the same result for the corner frequency as 1 over RC.